Hi folks, my name is Misha Evtihiev. Right now I work as a computer science software engineering researcher at JetBrains at ML4C and ICTR Labs. But before that, I did my PhD in theoretical physics in Israel at Weizmann Institute. And so today I'll give you a pop talk on string theory, on what is it and why we are interested in it. And it will briefly be as follows. First, I'll start with an extremely brief introduction in the theoretical physics nowadays, and why we believe what we know for sure is not enough. Then I will move on to the problem of black hole entropy, for which I will have to describe what is a black hole and what is entropy. And afterwards, I will move on to describing what string theory is and what are its foundations. And then I will present a construction in string theory, which kind of explains and solves the black hole entropy problem up to a point. And then I'll finish the talk with some more open questions. All right. So let's start with what we definitely know. So what we definitely know is that the world is made of elementary particles. And we definitely know that these particles can be explained with a framework called quantum field theory. Now, let me, and the particular quantum field theory that explains these particles is called standard model. So let me unpack this statement. So, quantum field theory is a framework that has the most fundamental entity in it of quantum fields. So let's break this down further. A field is something that is defined at every point in space. So imagine like temperature. Temperature is not a proper field, but still. It's plus 24 or so here, it's plus 15 outside, it's plus 36 somewhere right here. So you can define a temperature at every point in space. Okay? Unlike, say, I don't know, position of a ball. A ball is either here or there, but it's not like it's all over the place. And when I say that the fields are quantum, it has two implications. Implication number one is that the excitations of these fields, of which you can think as of the ripples on a sea, the excitations of these fields correspond to the particles. And another implication is that it is impossible, theoretically impossible, to measure the value of the field and the speed with which this value changes at the various exactly. It is related to the uncertainty principle. So if you recall in quantum mechanics, you cannot measure the speed of the particle and the position of the particle at the same time. So same goes for the fields. So hence we get quantum field theory. All right. And so basically all the interactions between the particles we observe, say, the light reflects off this whiteboard. This is because the whiteboard has electrons and photons reflects off an electron in the whiteboard and comes back to our retina. All of the stuff can be described with the quantum field theory framework in the language of quantum fields. And this framework is extremely successful in that it can explain almost everything in terms of standard model. So let's move on to the standard model. So, okay, this is except gravity. So this is a standard model of elementary particles. So what do we have here? So here we have leptons, which definitely know the electron, and mu lepton and tau lepton are basically like electron but heavier. And we have neutrinos, of which you might have heard. And also we have quarks, of which you might not have heard, but which make the particles like protons, neutrons, and other stuff. So like proton is made of 3 quarks. Neutron is also made of 3 quarks. Okay? And basically, all these particles interact in different ways. So in our world, there are, depending on how do you count, either 4 or 5 interactions. So one is, which you definitely know of, is gravity, which causes Earth go around the sun and which will cause the thing fall down if I drop it. Another one is electromagnetic, and this one is pervasive. It's not only the interaction that governs the current going down the wire. It's also why I can hold this stuff in my hand right now. Because this stuff has electrons, my hand has electrons, they repel each other, so I can hold it. Okay. We also have strong interaction. The strong interaction is what holds atoms together and what holds protons and neutrons together. And it is different from the rest of them interactions because, surprisingly, it grows stronger when you try to pull things apart. It's a little bit like a spring. So it's technically impossible to pull a proton apart. The best you can get a proton and some new particles, but you cannot get just one quark separated. And there also is weak interaction, which in our world manifests itself in the radioactivity. So you're like, it's not the radioactivity which you get when you do an X-ray. That's a different kind of radioactivity. It's just some strong photons. It doesn't count. But say whatever stuff goes on in a nuclear reactor, the stuff is running because of the weak interaction, because of the atom decaying down, generating heat, and so on and so forth. Okay. And also we have this Higgs boson, which was discovered something like 10 years ago. And this is the interaction which gives mass to many of the particles in a so-called Higgs mechanism, which we will not discuss today. That's a story for a different lecture. But, well, yeah. So the stuff that we have in standard model describes pretty well the strong interaction up to a point, but it kind of works. We can't compute things exactly, but we can compute things numerically pretty well. It describes electromagnetic and weak interaction really, really well. It also describes Higgs really, really well. So, but then there is a problem with the gravity. The gravity doesn't really fit in standard model. Okay? So, it's basically people try to fit the gravity. If you try to fit the standard the gravity in the quantum field theory framework, it just doesn't work out. You get infinities over infinities over infinities. And while this by itself is usually not that big a problem for theoretical physics, in this case it very much is. You can do nothing about it. And one more thing that I would like to mention here is that the particles that make up the matter, such as quarks or electrons or tau leptons, they're fermions. And the particles which make up, which correspond for the interactions, like photon, Higgs boson, gluon, which corresponds for the strong interaction and stuff like that, they're bosons. So bosons are the particles which essentially you can have many of them in the very same state. While for a fermion, you can only have a single particle in a very same state. Loosely speaking, this is not true, but this is a picture. You can put many bosons at the very same place, but you can put only one fermion at the very same place. This distinction is going to be important somewhat later on. All right. So, as I said, there are two problems with there is a problem with mixing gravity in the picture, but you can say, well, maybe gravity is all different, so we don't need to have a quantum description of it. Turns out we need, because of the black hole entropy problem, which we'll get to later on. But for now, just believe me, this is a problem. We need to mix quantum mechanics and gravity. And second problem, on which we will not touch much today, is why do we have this particular set of particles? So have a look over here. We got plenty of them. And all you can see in this small script, you have this mass 2.2 mega electron volt, or I don't know, here 0.511 mega electron volt. And these values are just God-given, okay? They just come out of nothing. And this is something which physicists very much don't like, because essentially you have a huge set of constants governing your theory. And if you shift them just by a tiny bit, the whole world would fall apart. And I mean in a literal sense. You would not be able to have atoms. You would not be able to have anything. So this feels very much unnatural, and physicists are very much unhappy about it. So both of these problems are really conceptual. It's not like we can't explain some phenomena right now that we observe. Because, say, for black hole, we can't observe the entropic behavior right now in a direct fashion. And for the particular set of particles, well, we kind of have them. But these problems are really hard and conceptual. There are also some other problems, like how do neutrinos get their mass, but these are outside the scope of this talk. And these problems I believe to be somewhat easier, in the sense that we have better approaches to resolve them. All right. Okay. So, and what's gonna happen later is I will explain how string theory will kind of tries to suggest a way out of these problems. All right. So I said the words black hole entropy. In this we have two concepts, a black hole and an entropy. So let's unpack that. So right, let's start with the entropy. The entropy is a pervasive concept. It's one of the most important concepts in physics, as much as energy, and I would even say even more important than energy. Because in certain setups you can't properly define an energy conservation law, but you can define the second law of thermodynamics. If you consider some strange setup in general relativity, this is not impossible. So the entropy originates in thermodynamics. Like thermodynamics is a science of 18th century on how to build a heat machine, how to build a steam pump and stuff like that. And there is the so-called second law of thermodynamics, and there are many ways to frame it. And the most understandable way to frame it is that the heat doesn't flow from a warm object to a cold object for free. Okay? In simpler words, this means that your fridge does not work without electricity. We kind of know that. Now, we can reframe this statement in the mathematical words, and we can frame it in the way that there is a certain function which never decreases. And this function would be entropy. And so the second law of thermodynamics is the entropy of a closed system cannot decrease. Okay, so the time have passed, and theoretical physicists have discovered the science of statistical mechanics. It basically gives an explanation for what goes on in thermodynamics. And basically, in thermodynamics, the entropy can loosely be understood as a measure of uncertainty of a measure or a measure of disorder. Most probably you have heard these buzzwords. So what does this exactly mean? So imagine you have a gas cube, like a gas balloon, but today it is a cube. And it has some temperature, it has some pressure inside it, it has some volume. So all these properties are macroscopic, like you can measure them with your eyes. But they all are governed by the behavior of the molecules of air inside this gas cube. And there are different configurations of these molecules which can lead to the very same thing. So here is a picture, I'm not sure if you can see it well, but basically you have here many dots with the arrows. And the arrow depicts the speed of the molecule, and the dot is the molecule. So all these different microstates correspond to the very same gas cube, and basically entropy is related to the number of these microstates that correspond to the very same macrostate of this gas cube with a given temperature, volume, pressure, and all these other macroscopic properties. Okay, and so basically the more the states are available, the bigger the entropy. And you might know this statistical mechanics definition of the entropy, because this definition very much reminds of the definition of entropy in the information theory. And this is not a coincidence. This is in fact quite logical. But once again, we won't have time to discuss it further. All right, so far we know what is an entropy, so let's talk about the black holes. So this fine man with a very distinct mustache here is Karl Schwarzschild. He was one of the very brilliant German scientists and a man to which I can't even express my utmost respect, because he served at the First World War and he had an extremely painful disease. Nevertheless, being in the trenches with this extremely painful disease, he managed to write several papers on general relativity, and one of these papers introduced these black holes. And unfortunately, soon afterwards he died, but not after he sent his set of papers to Einstein. Einstein said this is total nonsense, And then he spent a couple of years thinking and said, well, probably it's not. And in fact, it's not. So what is a black hole? A black hole, from a technical point of view, is just a certain solution of the equations of general relativity. Like, general relativity is a framework that describes gravity, and it can have many solutions. So black holes are one of the solutions. So basically, this solution means that there is a region in space and time from which nothing can escape. Like a hole, and black because no light can go out. So, what do I mean by saying that nothing can escape? So, there is this notion of the escape velocity. So, escape velocity is the minimal velocity, minimal speed a free object must have to fly away from a body to an infinite distance. If you have played Kerbal Space Program or stuff like that, you know that to build a rocket and to launch it to, say, Mars, your rocket should be at least something like 12 kilometers per second to fly away from Earth. Well, I'm not sure about the exact digits, because I guess in Kerbal Space Program you also need to account for the air, but still. So, basically, the heavier the object and the smaller it is, the bigger is the escape velocity. So for Earth, the escape velocity is 11.2 kilometers per second, not accounting for air, but we disregard the air for the time being. For Sun, it's 617.5 kilometers per second. So you can compare that to the speed of light, which is circa 300,000 kilometers per second. So you can see that the Earth and the Sun are very far from being a black hole. But for the black hole, however, by definition, the escape velocity is exactly equal to the speed of light. So not even light can escape it. Okay, so far it's all just a funny construction, but in the 60s, people started gaining more evidence, and they kind of started thinking that it's not impossible that we really have a black hole in the real life. For example, in the 60s, astrophysicists discovered neutron stars, which are basically stars made of neutrons. Well, not only neutrons, but we have an expert on neutron star in the audience. Not me, so you can bother him with the questions. Not me, I'm not an expert on that. But nevertheless, neutron stars have escape velocity of circa 1/3 to 1/2 speed of light. And having seen that, people started thinking, well, maybe why not? Maybe we can have black holes. So they started paying more attention to the black holes. And the problem is, if you try to estimate the entropy of a black hole from a classic general relativity perspective, it turns out the entropy of a black hole is exactly 0, just by definition. And this is very much a problem, because if we have a black hole with entropy 0, we have something with entropy whatever, but definitely bigger than 0. We drop it into a black hole, we get a bigger black hole with an entropy still 0. So what happens is that, well, the entropy of the world decreases. This is very, very, very bad. I mean, like, the second law of thermodynamics is not something we want to be violated. So people started thinking on what to do about it, and then there was a brilliant Israeli physicist, Jacob Bekenstein, whom I had the privilege to meet, and he basically made a set of Gedanken experiments, the set of thought experiments, which didn't actually prove anything, but they gave a decent explanation that the entropy of a black hole should be proportional to its area. So in this nice equation I wrote is the letter A. Alright, so Stephen Hawking, about whom you must probably know, read these papers by Bekenstein and said this is nonsense. Then he spent a couple of years trying to figure out what's going on, and then he decided this is not nonsense at all, and he refined Bekenstein's result by adding the rest of the stuff here. So what's important here is that, so this is the entropy of the black hole, this is the area, and the rest are constants. So this is speed of light, this is Boltzmann constant, never mind, this is the stuff from thermodynamics, but it's constant, it's important. This is a gravitational constant, and this is the h bar, the constant from the quantum mechanics, the Planck's constant. Okay, so it seems like everything is all set. So we got the answer, why the hassle? So there are two problems with that. First, Hawking's derivation is thermodynamical. So it's like in good old 18th century, we don't count microstates, we don't explain from where does the entropy comes, we just kind of get an answer. This is bad. But what's even worse is that we got this h bar here. So this h bar is the sign that you have quantum mechanics. It's like whenever you have an electron charge, it means there is an electromagnetic interaction. Whenever you have g, the gravitational constants, it means you have gravity. And whenever you have h bar, it means you get quantum mechanics. What does this mean? This means that to derive this equation, you need to account for the quantum gravity. And the mere existence of h bar in here means that the quantum gravity does exist. Or we need to have another model of an entropy of a black hole, and so far we believe that there ain't none. We believe that Hawking formula is right, and there is no other formula that could describe that. So basically this is the strongest hint. We should be able to unite gravity and quantum mechanics. But however, we don't know how to do that, because as I said, quantum field theory doesn't really mix with gravity directly. It doesn't really work.
We put it with a bit what is S and
S is the entropy and A is the area. Area. I should refer to the Gedanken experiment there. So is there an easy way to describe that? No, I don't think so. Sorry.
Bound, because we think of like surface of for the sphere, and it is of area and volume should be.
No, I mean they should be related, but the question is very valid. Why it is proportional to the area and not to the radius or the volume? So, well, basically, the Gedanken experiments by Jacob Bekenstein are of the kind: I have one black hole, I have another black hole, they unite, so the area grows somewhat, and I believe that the entropy should grow somewhat, and stuff like that. And then he made a couple of more assumptions. I think one of the assumptions he made, which is actually very reasonable, is that the black hole is the object with the highest possible entropy, and from there you can derive this relation to the area. But I'm definitely not able to do that without a blackboard. So yeah, any other questions, folks? All clear so far? Well, brace yourself. Because we are moving on to the string theory. All right, so one thing to know about string theory, it didn't move straightforwardly. It had ups and downs, twists and turns. It moved in many different fashions, but still it is here now. So the first formulation of the string theory is due to Gabriele Veneziano, who derived that in 1968 when he was working as a postdoc at the very same university in which I did my PhD, or to be more precise, when he was on a yacht trip away from this university. So take the cue. So in 1968, there was a big problem nobody really knew how to solve, which is how to explain the way the protons scatter off each other in a collider. We know how to explain that now with a standard model, but by that moment it was an open question. So he introduced a model, so-called dual resonance model, but it doesn't really matter, because in 2 years, Nambu and other guys, and Nambu is a really famous scientist, he got his Nobel Prize, Nambu figured out that the quarks, the parts of the proton in Veneziano model, they look like strings, like they look like different energetic states of protons. They look as if the quarks are excited like the guitar string, like the basic excitation, the second excitation, the third, the fourth, and so forth. Okay, so hence they gave the name of the bosonic of the string theory, or to be more precise, the bosonic string theory, because the model by Veneziano et al. only could introduce the bosons into the theory, no fermions.
What does it mean, that particle?
So basically it means the spectrum, the energy spectrum of the proton, basically each next available quantum states comes like 1, 2, 3, 4, 5, and so on, so-called radio trajectory. So basically, like on a string, the energy of a string with these excitations goes on like 1, 2, 3, 4, so on. Right. Okay. So one really important thing here that we have is that these strings with which Venetian explained the proton scattering, they're non-local. And this is a huge distinction, because so far in theoretical physics, every interaction is local. Like you have two fields interacting, but still the interaction comes at every single point. At the very same moment of time, they interact at point A and point B independently. Here, not anymore. Here we have this very, very tiny strings of the order 10 to the power minus 34 centimeters, but which are not point-like, which are extended. And this makes a whole difference. And one of the important reasons why does it make the whole difference, because it means there is a fundamental scale beyond which we cannot go. And this is very important, because in most of the cases, infinities in physics and infinities in quantum field theories, they come from the moment when we try to account for smaller and smaller distances, like when we try to account for the distances which are arbitrarily close to zero. And here we have a fundamental scale, which is, first of all, some scale in our theory from which something else can arise. And second, we cannot go below, so in a certain sense, we cannot have infinities. Not exactly true, but, well, never mind. All right. So this is a nice theory, but it has many problems with it. Well, first of all, it has some fixed set of particles to exist, which is not bad at all, because we want some fixed set of particles to exist which come from in our standard model. But one problem is that there is a particle which, according to the theory, moves faster than light. This is a problem, but not as big of a problem as you might think, because technically in theoretical physics, this means that the theory is okay. We just need to rewrite it in a certain way, and in this certain way, this faster than light particle will disappear. Or, to be more precise, this means that the vacuum is unstable and decays to a stable vacuum. Yeah.
Why this particle moves faster than light?
Speak up, I can't hear you.
Why is this particle moves faster than light?
Basically, when you write down the set of the particles, you also write down the equations for the equations for these particles, and the equations are fixed from the fact you have a string theory. And when you write them down, you see that the equation of motion that governs this tachyon makes it move faster than light. It's just basically comes from like a feature of a theory. You cannot have it other way. All right. So here we say that whatever vacuum decays to a stable vacuum. So, well, okay, show me the stable vacuum. Well, we cannot. So we don't know how to build the stable vacuum in the bosonic string theory. So in essence, it's like this theory may be right, but we need to rewrite in a certain fashion. 50 years have passed, we still don't know how. This is not that terribly bad, but what is worse is there are no fermions in the model. So and thing is, if you don't have fermions in the model, you can't really explain the real world, because the real world is made of fermions. Like quarks are fermions, electrons are fermions, so how come? And this one is a big problem. And finally, which is not a big problem in fact, but which is something that made people uneasy, is that the bosonic string theory only works in 26 dimensions. Kind of happens because when you do the derivation, when you try to make everything not to be infinite, you need to sum 1 plus 2 plus 3 plus whatnot. And as every mathematician knows, this is minus 112. This is actually quite a decent mathematical statement that's the so-called analytic continuation of the so-called Riemann zeta function, but still which makes people uncomfortable. But this is all right for theoretical physics because the whole job of theoretical physics is to make people uncomfortable. And still, 26 dimensions is a little bit too far, yeah.
For why 26 dimensions is a problem, like our world is a three-dimensional space.
So you need to hide, well, three-dimensional plus time, so you need to hide 22 more somewhere. You don't see them around, so they should be hidden somewhere. We'll talk on that later. We'll definitely talk on that later. All right. So this is a dead end. And next come supersymmetric string theory, or for short, superstring theory. So to explain what is supersymmetric string theory, I'll need to introduce the supersymmetry itself. So supersymmetry is an idea that there is an additional symmetry in our world that relates a boson for every fermion and a fermion for every boson we see. So like it's easy to figure out that for electron we have selectron, for photon for TINA. So if you have a boson, on changes for INA, and if you have a fermion, you get an extra S in front. So this is a very beautiful idea because, and I want to explain that further, somehow this symmetry also mixes with the symmetries of our space-time, like translation symmetries. And this is the only possible symmetry that could exist in our world. Okay? The only possible way to extend the symmetries that we have, that we observe right now, like the translational symmetry, which says that the law of physics is same at every point, or time invariance, which says that the laws of physics are same at every moment of time. So yeah.
Another wall.
Not exactly. It means that in our world we could have selectrons, photinos, and stuff like that, but then, as it is called, supersymmetry is broken at a certain point, so they are different from these electrons. So naturally they should have the same mass, and same like electric charge, but that's not what we observe. So supersymmetry is spontaneously broken at a certain moment, but that's what we didn't find so far. We hope to find that sometime, but not yet. Yep. Any other? Yep.
Were any of these new violets?
Nope. If there would be, that would be a set of Nobel Prizes, and it would be way bigger than Higgs boson. Like, way big, I would say it would be as big as Higgs boson, gravitational waves, I don't know, like, what was another hyped thing as of late? Well, take these two and multiply by 10. This would be as big. Because it would be a new particle that is outside the realm of standard model that we have found. And the standard model had fixed itself in like 70s. So it's been like 50 years, since we didn't have an idea for how to add a new particle. Well, we had an idea, but we didn't find this particle according to an idea. There are plenty of ideas, but all of them either have not been proven right or already has been disproven. Okay, so supersymmetry is a very nice idea by itself because it can help us with extending the standard model, and it can help solve us some of the problems, like the problem of the zoo of the particles, because in supersymmetry we can kind of explain how did all these different masses appear. Once again, not going to describe that today. But still, we cannot find that yet, so it's still very much a conjecture, yet a very useful one. Well, all of the studies I did in my PhD were related to supersymmetry. So it's, in essence, it's even a bigger subject than the string theory itself. Right. All right. So let's move on to the superstring theory. So, well, what changes? First technical comment is that by now everybody calls superstring theory just string theory, because bosonic string theory doesn't really explain much. So the only reason you need it is to teach the students the simpler subject before you move on to the harder one. That's about it. It definitely doesn't really work. It's like a nice artifact from the past, so well, let it rest. So everybody calls superstring theory just a string theory, and I might say that from time to time later on, so please don't let me be misunderstood. All right. The main feature is that we have both bosons and fermions. Kind of could be expected, because as I said, supersymmetry relates bosons to fermions. In original theory, we had just bosons, so we should have had bosons and fermions, right? But this is very nice, because as I said, in the real world, we also have bosons and fermions. So this is a promising step up from the bosonic string theory. A nice feature is that we have graviton. So graviton is a conjectured particle which transmits a gravitational interaction much as photon corresponds for the electromagnetic interaction. And as we said, we want to have quantum gravity, we want to have graviton. So if our theory has graviton, this means that we got a theory of a quantum gravity, even if unrelated to the real world. This is huge, because superstring theory so far is the only kind of consistent theory. Don't pick me too much on my words here. The only kind of consistent theory that introduces, that has a graviton. I mean, string theory is consistent, but we don't understand quite a decent amount of things in it, so yeah. Yep.
What is the
Gravity, no? Not in the real world, but in superstring theory, yeah, definitely.
at least one about the symmetric pair?
No. We should have both. We should have both. But well, we observe gravitational waves, and gravitational wave to graviton is like electromagnetic wave to a photon. So in essence, I would say that we observed electromagnetic waves like in 17th century with all these diffraction experiments, but it took us a couple more centuries to observe the photon itself. So like, kind of same. I mean, I'm not saying we're going to observe graviton in 200 years, but still, like, there is a huge gap between observing waves per se and observing the corresponding particle. Yep.
As far as I remember, relativity describes gravity as the geometrical property of space-time.
Yep.
Does that contradict to presence of gravity field as field graviton as spot?
Nope. I mean, you have a all right, I got to need an integral to show that properly. But basically, what you happen to have is that. Just give me a sec. I need to try to explain that without writing equations. All right. So basic story is as follows: you get certain thing that explains your theory, and the certain function which is called Lagrangian, and this Lagrangian is integrated over the whole space. So when you don't account for general relativity, the space is flat. It's like dx, dy, dz, dt, you name it. When you get gravity, what you get is that instead of that, your space is whatever curved, and you get some different stuff instead of this dx, dy, dt, dt. But this doesn't by itself contradict that you have a gravity field. And that, in essence, is even present in general relativity. Like, general relativity could be summarized into words, into sentences. The first is matter tells space how to curve. The second is the curved space tells matter where to move. And the two interplay with each other. So technically, the matter which moves in the general relativity is described by, I don't know, electromagnetic, the quantum field of electrons, the quantum field of, I don't know, the boson, whatever. And nothing technically precludes us from having one more field for graviton. There is technically no contradiction in there. Not sure that I did explain, but as usual, it happens in theoretical physics and in math. You don't really understand the idea, you get used to it. Sorry. All right. So graviton is present, so you can have quantum gravity now. And this means, that you can have some theory that explains quantum gravity for you, which is super nice. What is not nice? What is not nice is that you need to have 10 dimensions. These 10 dimensions spring up in the very same way as we had 26 in bosonic string theory, but still 10 is 6 too much. And last but not least, there are 5 different ways, 5 different frameworks to write these string theories, which are called string theory type 1, type 2a, type 2b, heterotic, and H0, I forgot what's the proper name. So, and none of these is ideal, and they're all kind of different. So instead of having one theory, we have 5, one theoretical framework, we have 5. All right, so every theory of that is still better than bosonic theory, string theory, but still not ideal. So we'll talk in a few minutes on what to do with this 5 different theories, but for now let's discuss what can we do with the 6 extra dimensions. So here comes the most popular picture you get when you Google for string theory, and I'll go on to that a little bit later, but for now just admire how beautiful is it. It is really beautiful in my opinion. So right, in our world we have 3 spatial dimensions plus time, so we get 6 extra. So what do we need is that we need to wrap them up on such a tiny object that we cannot distinguish that from the with the tools we have right now. Like like a sphere that is so small that cannot be observed with any kind of a probe we have. Not with a microscope, not with an electronic microscope, not with anything we have. This idea is called compactification, and the simplest way to think of that is to say that okay, we have 3 dimensions in our real world. We have time, and we also have a 6-dimensional sphere, like a normal sphere, but 6-dimensional, and the sphere that is so small that we cannot see. And to imagine this better, imagine the surface of a sea when you're flying on a plane. So you know for sure the surface of a sea is not flat. It got waves, it got ripples, so it's actually 3-dimensional. However, when you're up on a plane, you're so far from the surface of the sea, you can't really see the waves and the ripples. It looks like it is flat. Same goes here. Like you cannot really see these compactified dimensions, and so that's why we that's how we get out of this conundrum. And actually, it is even nice that we can have compactified dimensions, because there are multiple ways to wrap these things up, and one of the most promising options are the so-called Calabi-Yau manifolds. Now, I won't explain what is a Calabi-Yau manifold, doesn't fit into the time frame, but what is important is as follows. First, it can have different amount of holes, like a donut has 1 hole, and Calabi-Yau manifold can have as many holes as you wanna, and the amount of holes corresponds to amount of particles one would get if one would try to write the standard model from a string theory compactified on the Calabi-Yau manifold. So basically, if you use a Calabi-Yau manifold with 3 holes, you can write a theory that is kinda similar to the standard model. It is kinda similar in the sense that, like standard model, it has 3 generations of particles. Just give me a sec. So here you can see that you have electron, you have muon, which is like electron but heavier, and tau lepton, which is like electron and muon but even heavier. So these things are called generations, like generation number 1, generation number 2, generation number 3. You can even see that here. So the number of holes in Calabi-Yau manifold corresponds to the number of generations in the standard model in the quantum field theory one builds from the string theory compactified on the Calabi-Yau manifold. There are 2 problems with that. Problem number 1 is that there is no complete classification of the Calabi-Yau manifolds, and mathematicians believe there might be an infinite amount of the Calabi-Yau manifolds. That's not a big problem, but the bigger problem is that the Calabi-Yau manifolds we have looked at so far don't really correspond to what we see in the real world. So basically we have looked at a set of them, and they do not correspond to what we see in the real world. Well, happens. Okay. Well, I also need to mention that Calabi-Yau manifold is not the only option. There are other options, but they're even more obscure in essence. All right. So, in 1995, a very nice person called Edward Wheaton, who I believe is the smartest theoretical physicist probably have ever been alive, suggested an idea to unite all these 5 different superstring theories that I have mentioned with the notion of the M theory. So one thing that I should immediately say about M theory is that we don't really know and don't really understand what is it. Happens. Nevertheless, it is kind of framework that generalizes all the string theories that we have, superstring theories that we have introduced so far. So you can have a look at this picture. So here you have M theory, like in general, and all these cusps, like all these particular setups of this M theory generate one kind of superstring theory. Type 2A, type 2B, E88 heterotic, whatever. And this M theory is generalization of all of them, and it is the most promising candidate for the theory of everything. So the problem is that we have some understanding for this type 2A, type 2B, like for these superstring theories themselves, but we don't have like even remote understanding for the M theory proper. And I mean, it was a very important thing because it started a field of study which related different superstring theories to each other, like type 2A to type 1 to type 2B to whatever, with the so-called dualities. Once again, unfortunately, this is completely out of the scope of this talk. But it nevertheless moved us forward in understanding that these 5 different superstring theories are in essence very much related to each other, and up to a point could be thought to be the same expression of the same thing, which we don't really understand right now. One more thing that came up together with the M theory is the so-called branes, on which I will talk right now. And a brane is basically a generalization of a string. So more on branes. Brane, a shorthand for the membrane, is like a multidimensional object that generalizes the idea of a string. And the original way in which it was introduced was as follows. Like, there are 2 options for a string. A string can be open, like this one, like a loose here, or it can be closed, like a loop. So if you have an open string, it has 2 loose ends, and they can end somewhere, right? And Polchinski and other folks have thought that, well, maybe the ends of the strings, they end on some kind of a surface, and this surface moves, somehow moves as a string move, and somehow and somehow does some stuff, and so on and so forth, much like on this picture. So we have here different strings, like this one has 2 ends attached to the very same brane, and this one connects 2 different branes, and so on and so forth. And so originally it was an idea that, okay, we have strings, we have surfaces to which these strings could be attached. We call these things branes. Well, kind of useful to describe things. Let's go with that. Any questions so far? Okay, how many of you did I lose on the go? Not so terribly bad. Yeah.
I have a question. But what is take the reason of what string is? It's more like a model of some energy configuration of the particle, right? And now we have actually discussing their forms of something. Can maybe?
Yeah. So okay. So basically, the setup is as follows. Let's go way back further. Way back earlier. We had quantum fields, and we said we have particles. So each particle is an excitation of a quantum field. But whenever we discuss what goes on in the real world, we don't write particles. We write corresponding quantum field, and we say that it behaves in a certain fashion, interacts with the other quantum fields in a certain fashion, and the basic excitation of, say, an electronic fermionic quantum field is an electron, but then it can get you many different what's the name? Sorry, I forgot the name. It can get you many different particles which are born and die immediately. I forgot the proper name, and so on and so forth. But still, the quantum field theory is a framework which manifests itself in the particles. Same with the string theory. It's a framework, but instead of a field which is defined at a certain point, you have like a field which is defined like with not with a point, but with like stringy things. And the way this stuff is expressed in the real world is well, the particles we see, or so we hope.
So Okay, it's just we define like some properties of a field not over one, but over some geometrical construction that we start to, and then we get into the details in which space could define it.
Yeah, okay, so let me maybe rephrase it in this way, maybe it's going to be more obvious. So, okay, a field, loosely speaking, is just like a function. It takes a point in space and gives you a number. If we are talking about, say, temperature, which is not a field, but never mind, or it gets you a vector, which is the case with the electric field. Or, in this case, you can argue that, well, it's not like a field in the proper definition of field, but still it's kind of the same. You get an this small extended object. So basically, this is a kind of strange mapping between the space we live in and the stuff we...
Like for every point where field is defined, and maybe not generatable, we define that there is a shape that has some property.
Well, I mean, it's all mathematical framework in an essence. You don't have, I mean, you do the math, the magic happens, then you get the answer, and then you relate this answer back to what happens in the real world.
Just plus the question where the
Yep.
I couldn't quite put this answer. So, basic quantum theory says that the field is real thing, and the particle is like a particle.
Yes.
And string theory says that some is string, so something real, and particle side effect.
Well, define real. I'm being serious, because you cannot measure the field directly. You can only measure the stuff like particles and stuff like that. So if we are talking about what is real, I would say that the particles are real. If we're talking about the description, then I would say that in quantum field theory, the proper description is in terms of fields. In string theory, it's in terms of strings. And how we get from strings to the quantum fields, it's another different story called ADS-CFT. Basically, you can relate the string theory to a quantum field theory with a certain construction. Once again, outside the scope of this talk, have that on an additional slide, but gonna take us 20 more minutes. But basically, there is a decent construction, and this construction even works very, very nicely to explain some things in theoretical physics, which are not related to the real world, but still the things that theoretical physicists study. And these things are not related to the string theory per se, but this makes you like a different way to think of this theoretical physics concept, and you can understand it with the string theory better. So like some of the papers that I wrote on superconformal field theories, they were advanced by some string theory constructions. It was because these string theory constructions allowed us to get some certain superconformal theories. Okay? So basically, yeah.
Can we go backwards once?
Sure. Yep. One more?
Yeah, I don't quite understand. So we that the 6-dimensional space is in a space into this small manifold.
Oh, why? No, not necessarily infinite. It could be. Well, I mean, you could live on a like. It doesn't have to have infinite volume by itself. You just need to have extra dimensions. It's like, like on a sphere. The sphere is very much finite. Still, it has two proper dimensions. Or like on a cylinder is infinite. Like a cylinder is infinite in one direction and very much finite in another. So it's.
But the result is that the whole matter consists of the infinite number of this tiny manifolds.
No, it's like, imagine you live on a needle, on a thin needle. In this, would you say that you live on an infinite amount of very small circles, or because it's exactly the analogy here? You have a stuff which is very much elongated in one direction and a very small circle. So pretty much like that. These manifolds are very tiny, you can see them, and they're just in the other dimensions. So it's not that the matter is made of that. It's just that the whole to describe the space at every to describe a point in space, you need to say name the time moment. You need to give 3 spatial locations, and you need to give 6 coordinates on this Calabi-Yau manifold, of which you don't really care because you can't really see them. All the coordinates seem to be the same to you because they're just so close to each other you can distinguish. Any better?
This is like global coordinates.
Oh, yep. Right. Yep. So getting back to brains. As I said, for starters, these are just some surfaces on which the loose ends of the strings end. But then with further studies, physicists found that these branes kind of behave like strings. They can have mass, they can have tension, they can have electric charge, and so on and so forth. And whenever you add some set of branes to the theory, it also affects the set of particles you have in this theory. Much like we had with the string theory. We added strings, we got some set of particles. We also add some set of branes, we get some more particles. So this is how this kind of makes impact in the real world, because particles is once again what we can probably measure. So this is nice. This means this brain stuff is kind of important. And one more thing, the reason why I talk about brains today is that they allow us to do a construction that will allow us to have a black hole. So let's talk about that. So we can have some brain construction that is called black P brains. Some kind of a brain, doesn't really matter which one. And it has a very strange geometry. So when I say P is a number of the dimensions. So in this P spatial dimensions, it behaves like, well, normal surface, like plane, sphere, Calabi-Yau, you name it. But in the rest of them 9 minus P spatial dimensions, it behaves like a black hole. Okay? So when we get some set of these branes, we basically get a stuff that behaves like a black hole in 9 minus P dimensions. Okay? And why does this matter? Sorry?
Why 9?
10 dimension is 9 spatial plus time. And why does this matter? Because then we can compactify these brain dimensions in which it behaves like a brain, shrink it to a very small thing, and say it is so small we don't care. And in this way we get a theory in which we don't care about these P proper dimensions. We compactify them away, and we have this 9 minus P dimensional theory in which we have a black hole. So we have a string theory set up. We wrote some string theory. We threw in some P branes for a good measure. Then we said that our 10-dimensional spatial world looks like time plus P dimensions which live, say, on a very small sphere, doesn't really matter, and 9 minus P, which look like a black hole. So this is a black hole in stringy world. This means we can have a black hole in stringy world. This is nice. What is even nicer, and what Strominger and Waffe did in 1996, is that they considered a certain combination of these branes to get a 5-dimensional black hole, and they computed entropy for this black hole. And they computed the entropy for this black hole in two different fashions. First, they computed it like Hawking did, in the very same approach, like thermodynamical way, and they got Hawking formula. Second, they computed the entropy in the honest way by counting microstates. So reminding you, the microstates here are different setups of like small details of our system which don't manifest themselves on a large world scale. Different setups that all look the same on a large scale. So they computed the entropy of a 5-dimensional black hole in a proper way by counting microstates, and the two results matched. And this is huge. Why this is huge? Because we get a theory of quantum gravity, because as we said, string theory is a quantum theory and it has graviton, so it is a theory of quantum gravity. And we have a black hole in it by construction of Strominger and Waffe, and we compute the entropy in it, and we get the right answer like the one Hawking did, which we believe to be the right answer. So this means string theory can explain black hole entropy. And in essence, this is the high point of this talk, because basically Strominger and Waffe tell us that we know how to address the black hole problem, entropy problem. But no. So what is the big deal? Well, first thing you can notice that we have 5 dimensions and we live in 4. That is already a little bit of a problem. Second problem is, well, you may recall that we talked about
Here, 5D is 5 dimensions of space.
5 dimensions of,
Or please,
5 dimensions, 5 dimensions of space, sorry, 5 dimensions of space, 6 dimension proper. So that's already not so good. What's even worse, and that's not very much not nice at all, that as we said, we have supersymmetric supersymmetric string theory. So in this setup, we also have supersymmetry, but we don't have supersymmetry in real world. So go figure. It doesn't really match. So basically, we can explain an entropy of a certain black hole, but this black hole has nothing to do with the real world. So this paper is like 26-year-old, and there have been many studies on that afterwards. Even I wrote a paper on this subject, but we are still not much closer to the solution. Like, the real world black holes are still very far away from the ones that we can explain. Yep.
Function formula for entropy
Is
extended to like 80 dimensions.
Yep. You can extend it to any dimension. Okay, so we are moving on towards the end of the talk. I ain't gonna bore you for much further. And right now I'll talk about one of the biggest problems of the string theory, which is a problem of the string theory landscape. So, as you have asked, string theory has strings, and in our world we describe everything with fields, so how do we match each one to the other? And the answer is that we kind of can do that by building by considering certain compactifications of string theory. We can do that. And the problem is there are many ways to skin a cat. Too many ways to skin a cat. Like there is a very large number of choices we can make to get quantum field theory from a string theory. There are different estimates. Some people say it's 10 to the power of 500. Other people say it's 10 to the power 272,000. In any case, that's too much, because considering one case takes like several months of a work of a theoretical physicist. It's not all that bad, because there is a strong belief that most of these cases are irrelevant to our world. There is a so-called swampland conjecture that says that most of these cases are irrelevant, but still it doesn't really answer much, and it doesn't really explain us how to choose. And there are 2 problems with how to choose. First, we want to find this choice. We want to build the standard model out of string theory, and we don't know how to choose. The second, which is once again a very conceptual and very important philosophic problem, is why this set of parameters. Why exactly that? Because we can, let's say that we know the exact answer, we plug this in, we get our standard model, but let's say we shift these parameters just somewhat. If we shift these parameters just somewhat, we get some different model, which is not standard model. So why did we end up in a world which is described by standard model and not something else? This problem is largely philosophical, but it's one of the problems that keeps physicists from sleeping sound at night, because it's like makes you very much uncomfortable knowing that the whole world is existing just because of a very particular throw of the dice of a very particular set of parameters. And one of the options to get out of that is the so-called entropic principle, which is like, well, if the constants would be different, we would not be here, but we are here, so why do we bother? It is a serious approach in the sense that many theoretical physicists believe in it, and many don't. So there is a huge divide around it, but still, it's like people are really strongly divided on that, and everybody would be really happy if you would find an explanation which would not be an entropic principle. All right, so let me now talk a little bit on what comes next. So going a little bit meta. So first, as many other fields of science, string theory has experienced its ups and downs in the development. I would say that right now it's stagnating. So there is the biggest conference in theoretical physics called Strings. But if you look at the lineup of this conference, in the last years, most of the talks have not been related to string theory at all. Well, I mean, they still didn't manage to rename the conference or didn't even manage to create a good name for a field. It's not string theory because many people do not do string theory. It's not high energy theoretical physics as it used to be because most of the cases is low energy. It's like, well, theoretical physics, whatever. So anyways, string theory is not so popular now, and this one is a little bit of a vicious circle. When it is not popular, you don't get too many grants. When you don't get too many grants, you don't hire too many young PhD students and postdocs who actually develop the science. When you don't have enough people to develop the science, it stagnates. So I'm not very optimistic about string theory future in coming 5 to 10 years. However, it's not the first time. I think it's like, well, we had first superstring revolution, we had second superstring revolution. I think it's the third time the string theory is stagnating. And I think at a certain point there will be found a way out. And I'm fairly optimistic that I will live long enough to see how string theory explains at least parts of the standard model. Well, it will not, I don't believe it will be proven in my lifetime, because to do that we need to do very exact experiments. But I believe that we will have a huge breakthrough, after which people will, well, it will be like with the standard model when we didn't have the Higgs boson. Everybody knew the Higgs boson is somewhere there, everybody knew it's kind of going to be working, but we just didn't have all pieces of the puzzle. But we were perfectly sure it's gonna happen sooner or later. So I think same will, well, I'm optimistic. I believe same will happen with the string theory in my lifetime. Okay, so I would also like to mention that I barely scratched the surface. So I mentioned the string theory dualities, didn't even say anything about it. I didn't say anything about the ADS-CFT correspondence, which is arguably the most important thing we get out of the string theory, which is arguably it's even more important than the black hole entropy, but it's kind of harder to introduce and harder to explain why it is important. And there are some other nice things which I didn't talk about, so, well, don't consider that to be a be-all and all introduction to string theory. It's more like one reason why we can be interested in that. So this is a QR code for the feedback for the lecture. I would more than welcome any of your comments you might have. And thank you for your attention. We still have some time for questions, so if you weren't brave enough to ask me during the lecture, that's your time. Yep.
So as far as I understood, there are no direct experimental evidences of string theory, and you mentioned that to prove it, we need to conduct some specific experiments. What kind of experiments are they?
Okay, so basically they could come in two fashions. First, we could relate to the black hole entropy. So the problem with the black hole entropy is that to prove that the black hole is entropic, we need to capture the black body radiation of the black hole. The black body radiation, the black body here does not relate to the black hole per se, just the normal heat radiation out of whatever. So to capture this heat, it is extremely hard to capture this heat radiation from the black hole, because somehow the bigger is the black hole, the weaker is the radiation. And all the black holes we have in the real world are big enough that it is very, very hard to capture that. Another option is to have some new particle which is outside the framework of the standard model, but which falls down inside the framework that string theory suggests. But to have that, first we need to capture such a particle, and so far we had no luck with that, and we probably most probably ain't gonna capture this particle at the LHC. And the next collider we're gonna build is gonna be built probably in 50s or 60s. Because it takes a long time to build, and we ain't building anything right now. Yep.
Great. Here on expansion to the black hole radiation.
Yeah.
Could you explain how it can radiate if the classical black hole nothing can escape from it?
Basically, in a In an essence, it is a quantum effect. Well, do I have a black hole here? Well, let's say this is a black hole. Let's say this is a black hole. So what happens here is that, let's say that this Earth we draw here is a black hole surface, and this circle line is very close to the surface of the black hole. So what happens in the world is that we have particles that are constantly created and annihilated in the vacuum, like, for example, photons. And what can happen near the black hole is that you have a pair of photons, and one photon is absorbed by the black hole and another one flies away. So this is one of the mechanisms in which the black hole, well, this is a mechanism in which black hole can radiate. There may be something else, but I'm not ready to discuss it. Been too long ago.
Principle, so that one of the particles
falls in, the other flies away. Yep. You had a question, I think.
The same version. The first person, what can happen to Momsen theory in the full?
To move the theory forward? Two things. First, three things. First, we can have a nice Calabi-Yau manifold which gets us something like a standard model, more like a standard model. This would be very promising. Even more. Second, we can understand M theory way better, and this will understand what the string theories better, and will understand what goes right and wrong in them. Third, we may be able to explain the real-world black hole entropy with the string theory. Fourth, we may be able to expand the swampland conjecture and prove there are in fact not too many options. And if there are not too many options, if there are like 10 to the power of 5, it's actually way better, because in this swampland conjecture, what we have is that we throw away some of the options immediately because they're total nonsense. We're not saying that the rest are not total nonsense. We're just saying that some of them we can throw away immediately. So if we have not too many options that we can theoretically go over manually, we can hope that most of them will be nonsense, and for the rest of them we could explain why we have this world and not the other. But we're still very far from it. Yep.
About black hole entropy, does it have any structure, and how can it have microstates which we count, and how does it have entropy?
So black hole in the string setup is basically made of these branes, and these branes can interact with each other in different fashions, which still manifest outside as a black hole. To give you proper details, I should probably go to a Strominger-Waffer paper, which I didn't go over for quite a while. But basically, you have a set of p-branes, which is they interact with each other somehow, but this doesn't manifest outside the black hole, except for you have a black hole. And all those different setups give you different microstates. You had a question.
Yeah.
Are there any experiments or maybe equations that can completely disprove the string theory?
A good one. Let me think a bit. Not as of now, just because that's one of the main beefs with the string theory, is that it is so flexible, you can get almost anything out of it. So the string theorists themselves are not too happy about it, and they're trying to bring the understanding of string theory to a point in which it will be possible to do that. But right now, not so far. So that's why I said that this is a framework, like pretty much quantum field theory is a framework. It's just the way to go, but it's not a physical theory. Standard model is a physical theory, and quantum field theory is a framework. It's like, differential equation is a framework, but Newton's second law is a physical equation. But you can write many other different differential equations, and most of them will not be related to the real physical world whatsoever. Same happens here. Any better? Yep.
Yeah. So, so
Yep.
Right? And with that part,
Yep.
what the whatever copy will have it?
It will fall inside the, well, okay. There is a simple and dishonest answer to that, and the honest but non-describing answer. Simple and dishonest is that it gets eaten by the black hole. And more honest answer is that there are some issues with understanding what the black hole is, and there is a very nice paper on the so-called firewall paradox by Almheiri and other folks. Once again, not going to describe that, that's a topic for yet another lecture. But basically, it turns out that black holes and quantum mechanics as we know it per se don't really mix well with each other. And there are three things, into all of them we believe, and we kind of believe in all of them, but they cannot be true simultaneously. So the thing in which it is easiest to not to believe, it is that on the border of a black hole, very close to the border of a black hole, there is something very special called firewall, like a wall of fire, which is a very special thing. And the two other options are way worse from the point of view of physicists. One is the quantum mechanics is non-unitary, which is basically means it doesn't have the symmetries we really believe it has. And another option I don't recall well, but still. So well, long story short, in classical general relativity, it just falls in, you never get it out, end of story. When you try to look more closely into that, you get a set of problems. People are thinking on that, and there is a very nice paper on the firewall paradox, which is kind of accessible and kind of understandable, in which it says that it's really a problem. Any other questions? Yep.
Question, did you quite something improves a lot the force principle of the
Yep. So this is ADS safety correspondence number 1, ADS safety correspondence number 2, introduction to the couplings, which is a very basic thing in quantum field theory. So basically the strong and the weak depends on, is computed from the value of this coupling, which is how fields interact with each other. And then I'm talking about dualities and string theories, because to talk about the dualities, you need to introduce what is a coupling. But I mean, it took me an hour and 10 minutes to introduce to give this talk, so I did know I am going to have time for it. Any other questions, folks? Yep.
Does it help you somehow in work?
Well, I would say if you did a PhD in theoretical physics, you get several things. First, people kind of believe you are smart. I mean, might be true, might be not, but you don't want to disprove that one. Second, you kind of know that you should not be scared of things, because how does theoretical physics work? We don't know what's going on, so we have some physical problem, and we try to throw different math at it. And for pretty much every area of math you can think of, it has been tried in theoretical physics. Number theory, check. Algebraic geometry, check. Differential geometry, obviously, yes. Algebraic topology, yes. Category theory, I think even that got into it. I think that for almost anything you can find something. And this means that you're exposed to lots of different math, and you're exposed to that as a physicist. So you're not really supposed to understand things deeply. You're supposed to make them work. And then it turns out that you can work with the things you don't really understand, and that's a huge benefit in work. So yeah, if any of you think of getting a PhD in theoretical physics, that's fun. Well, fun and very much not fun at all, if you know what I mean. So yeah, let's call it a day. Once again, thank you very much for coming. It was a pleasure having you here.